We'll start out by looking at some ionic bonds. And this says draw the Lewis symbols for potassium and for chlorine. So the symbol for potassium is K. That's a bad start there. And how many valence electrons does potassium have? It has 1 because it's in group 1A. So 1 valence electron. I'm still not happy with that size. That's a little too big. That's better. It doesn't matter which side, top, bottom, right, or left, that you put the electrons on. So there's potassium. Sorry, I accidentally paused it again. Oh well. Why don't we draw those in there? I think it would be really confusing if suddenly we were bringing up lower core electrons, right? The way Lewis structures work is you start with these valence electrons, and those are the only ones you're going to deal with. And so when a metal loses all its valence electrons, we don't draw the dots in. We just understand that underneath is another full layer. Any questions? So we can use Lewis symbols to predict the formula for compounds, ionic compounds. So we're going to do magnesium and nitrogen. So we'll start by drawing the Lewis symbol for magnesium. So magnesium, how many valence electrons does magnesium have? 2. And for nitrogen, how many does nitrogen have? 5. So how can these guys cooperate so everybody can have 8 valence electrons? Well, magnesium's a metal. It wants to lose those 2 electrons. So it's looking for somebody to take them. The nonmetal likes to take the electrons. So the nitrogen here is willing to take magnesium's electrons. So we put 1 over here and put 1 over here. Now magnesium has a charge of 2+. And what would this nitrogen have a charge of? -2. Is the magnesium happy? Does it have an octet? It does, because we cleared off the partial layer on the outside. Does nitrogen have an octet? No. It's closer, but it's not happy yet, right? Well, if there's 1 magnesium atom, there's probably a whole bunch of other ones around. So let's see what happens if we bring another one into this. So here's another magnesium atom. So this nitrogen is looking for 1 more electron, right? This magnesium is trying to get rid of 2 electrons. So the nitrogen is like, well, I'll take 1 of them, but I don't need both. Just give me 1. And well, better to get rid of 1 than none, right? So now this nitrogen has a 3- charge, and it got its octet. And this magnesium now has a +1 charge. Not happy yet. Well, if there's 1 nitrogen, there's probably a whole bunch of other ones. So let's pull in another nitrogen atom. Nitrogen atoms have 5 valence electrons. And so this is like, well, I'll take that electron from you. So we do that. And now this is 2+. Is the magnesium good? Does it have an octet? It's not showing, but we understand that there's 1 underneath. Now this nitrogen gained 1 electron, so now it has a -1 charge. Still not happy. It's like, this is going to go on forever, right? No, we're almost done. Oh, we need another magnesium atom. 2 valence electrons. This nitrogen needs 2 more electrons, and this magnesium wants to get rid of 2 electrons. So this is 2+, and this is 3-. So what's the formula then? We need 3 magnesiums for every 2 nitrogens, in order for them to be able to pass these electrons off and make everybody happy. So it's Mg3 N2, which we learn to do much faster just by looking at the charges. But here the Lewis model is showing us why those ions have those charges, right? And how that works together. Any questions? Mm-hmm.
How do we know where to put the electrons? Like when you write the N, you put like 2 and then 1, 1, 1.
Usually there will be, like there's going to be up to 2 on each side, right? And so usually you draw them singly first and then pair them up. I did draw the magnesiums paired up because they're in the s orbital, but if you drew them separately, that would be fine. We'll see later that these 4 correspond to an s orbital and 3 p orbitals, and that's where the 8 electrons come. Yeah. Any other questions? When ionic compounds form, the reaction is generally quite exothermic. So here's the formation equation for 1 mole of sodium chloride from its elements in their standard states. So we got sodium and half a mole of chlorine, and we make 1 mole of sodium chloride. The heat of formation is negative 411 kilojoules per mole. It releases that much energy. So where is that energy coming from? We can look at ionization energies and electron affinities. Because what's happening here is the sodium is going to lose an electron to become the sodium ion. And so we know the energy involved in that. That's the ionization energy. That's positive. You have to put that in. And then half of these are going to get an electron. So that's the electron affinity. That is negative. But if we're just considering ionization energy and electron affinity, we add those up, and this predicts that making a mole of sodium chloride would absorb 147 kilojoules, not release 411 kilojoules. So there's something missing. And what's missing is the lattice energy. So lattice energy is the energy that's associated with the formation of a lattice of alternating cations and anions. The potential energy is lowered when the opposite charges come together. And when the energy is lowered, the energy that it had before has to go somewhere, and so that gets released as heat. So this is an important statement here. Formation of ionic compounds is not exothermic because the metal wants to lose an electron and the nonmetal wants to gain an electron. We talk about it that way. I talk about it that way, and I will continue to talk about it that way. But that's not where all the energy is coming from. The release of energy is from all of those newly formed ions coming together, being all attracted to each other. You know, like magnetic toys, and they go click, 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 and they all stick together, right? Do you have to make them do that? No, they just have to get close enough, and then they snap together all by themselves. So here we have gaseous ions. So we've turned sodium atoms and chlorine atoms into ions, and they're all in the gas state, and they're going to be attracted to each other, and so they're going to go, whoo, just come together, right, and make this sodium chloride crystal. And it's got these like red, I don't know, it's not really flames, but it's really hot, right? It's releasing a lot of energy when that happens. Most of that energy, well, actually all of the energy emitted is coming from that lattice energy, and some of it actually went into the difference needed between the ionization energy and the electron affinity. the easiest way to calculate the lattice energy is with what's called a Born-Haber cycle. So this is a hypothetical set of steps representing the formation of an ionic compound from its constituent elements. And this is going to take advantage of Hess's law. So we're going to choose steps where we know the heat of formation for those things. We also need to know the overall change in enthalpy for the formation of that substance. So what does that look like? So this is sodium chloride again. So we're starting right here, this solid sodium and gaseous chlorine, the elements in their standard states. When they react and form sodium chloride, we can measure the enthalpy change, the heat of formation. That's published in books. It's available lots of different places. We can look that up. Okay. What we want to find is this lattice energy, and we don't have a way to directly measure that. But what we can do is we can imagine, well, what are the individual steps that would have to happen in here for this to become sodium chloride? Well, here sodium was a solid, so sodium needs to go into the gas state. Well, we can look up that value, how much energy it takes to vaporize a mole of sodium atoms. And then this half Cl2 molecule, we need to split that into chlorine atoms. And we can look up how much energy it takes to break those molecules into atoms. And then we can look at the ionization of gaseous sodium. So sodium likes to lose electrons, but it doesn't just drop them off. You have to put a little bit of energy in to pull them off. It's just that it doesn't take much energy. So we have to put in a little more energy to make sodium into an ion. We also need to make chlorine into an anion, and that's a negative process. That's the electron affinity. So that actually releases some energy. So we know all of these steps, and what we don't know is here. Taking the ions in the gas state and forming the solid crystal, what's the energy change there? That is the lattice energy. And so we can just look at all of these and find this missing piece. So there are trends in lattice energies. One of these has to do with ion size. Here looking at different metal chlorides, lithium, sodium, potassium, and cesium, and the lattice energies for those substances. The largest lattice energy, the most negative, is for lithium chloride, and the smallest is for cesium. Well, these are the alkali metals, and they get larger as you go down the group. Cesium is the largest ion, and lithium is the smallest ion. And we're looking at them paired up with chloride ions, so the chloride ion is the same for all of these guys. So we can look at the difference, the distance between the nuclei of these two ions. And the distance is the smallest for the smallest ion. And it's the largest for the largest ion. Because you have to go further to get to the middle of this guy than to get to the middle of that guy. When we talked about Coulomb's law, we learned that the energy is proportional to 1 over R, R being the distance between the things. So if the distance is small, the energy is larger. If the distance is large, the energy is smaller. These ions can get closer to each other, and so their lattice energy is greater. Any questions? Yes?
For that one, so we don't take into account the negative sign as like a negative number, right? It's like bigger.
The negative sign on the energy? Yeah. So here, the negative sign is just telling us which direction the energy is going. And it says that when this forms, the energy is leaving the lithium chloride. Good question. Negative things can be confusing. The charge on the ions also has an effect. We learned from Coulomb's law that the energy is proportional to the charge on one thing times the charge on another thing. So here, if we're looking at sodium fluoride and calcium oxide, these were chosen because they have a similar distance between the nuclei, 231 and 239. Pretty close, right? But the lattice energies are very different. This one's negative 910, this one's negative 3,414. Because here, the charges are plus 2 and minus 2. Here, the charges are plus 1 and minus 1. So if we're looking at Q1 times Q2, for this one, it's negative 1, and over here, it's negative 4. So just looking at that, that predicts that the lattice energy here would be roughly 4 times larger. And it is in that ballpark. Higher charges are more attracted to each other. The more attracted these things are, the larger the amount of energy they release when they come together. So lattice energies become less exothermic. They release less energy when the ionic radii increase. They become more exothermic. They give off more energy when the charges get bigger. So this is the kind of question that could show up on an exam. Arrange the following in order of increasing magnitude of lattice energy: lithium bromide, potassium iodide, and calcium oxide. So there are 2 trends here. One has to do with ion charge, the other has to do with ion size. The ion charge is the most important, so let's look at that one first. So what's the charge on a lithium ion? Plus 1. And a bromide ion? Negative 1. How about potassium? Plus 1. And iodide? Negative 1. That doesn't look like a plus 1 anymore. Okay. What about calcium? It's positive 2, and oxygen is negative 2. So if we're thinking about that energy being proportional to Q1 times Q2 divided by R, this is going to be big, right? The product of the charges is 4 times higher than for these guys. So that tells me that this is going to have the largest lattice energy. And we're going of increasing magnitude, right? So we're going from smallest to largest. So calcium oxide is going to be the biggest one. And then we got to pick the other 2 to fit in there. Well, these have the same charges, so now we're going to look at size. So here we have lithium and potassium. Which one is bigger? Potassium. So potassium is bigger. And then let's look at the anions. We have bromide and iodide. Iodide is bigger. So this one's also bigger. If the ions are bigger, does that make the lattice energy larger or smaller? Smaller, because we're dividing by that distance between the 2. So the bigger ions are going to have a smaller lattice energy, and it will go Ki and then LIBR and then CaO. Any questions? always good to ask if the model explains actual observations. And this ionic bonding model does. So ionic compounds have high melting points, and this is due in large part to non-directional bonds. So they are attracted in all directions. So it takes a lot more energy to cause them to melt. Non-conductivity of ionic solids. So if you try to pass electricity through solid sodium chloride, nothing's going to happen. The light bulb will not go on. There are no electrons, there are no charged particles that are free to move, and that's what we need to have to conduct electricity. Charges have to move. Nothing's moving here. But if we take this and we dissolve it in water, now we've separated those ions and given them freedom to swim around in the water, and so salt water does conduct electricity very nicely. Any questions?